Hello, friends. My name is Timen, and I'm a chemistry tutor at ELEarn. Welcome to another chemistry video from ELEarn. This video is about electrolysis of molten ionic compounds. First, let's answer the question, what is electrolysis? So electrolysis is the decomposition of an ionic compound when molten or in aqueous solution by the passage of an electric current. Now, what's important to understand at this point is that ionic compounds, when solids, cannot conduct electricity because the ions are not free to move. Now, electrolysis is a decomposition reaction, just like thermal decomposition and photolysis. I understand earlier in your education, you have looked at thermal decomposition, where a substance is broken down into its components by heating it. Now, when we look at electrolysis, we are looking at breaking down an ionic compound when molten or in aqueous solution by passing an electric current through it. Now, electrolysis uses direct current, that is the form of electricity that is supplied by batteries and cells, which means we have one side that is positive and another side that is negative, and electricity is going to flow in one direction only. Now, when we look at conventional electricity or conventional current, we're looking at electricity that flows from the positive to the negative. Now, let's look at the electrolytic cell. Now, here is a diagram of the electrolytic cell, and we basically have three components. We have the battery, which is the DC source. We have the electrodes. Now, under electrodes, there are two types. We have the anode, which is the positively charged electrode. This is the electrode that is connected to the positive of the battery. And then we have the cathode, which is the negatively charged electrode. And this one is connected to the negative plate of your battery or cell. Thirdly, we have the electrolyte. Now, when we look at the movement of the electric current or the movement of electrons, you will see that your electrons are going to flow from the anode through the battery to the cathode. So what the battery does basically is to pump electrons from the anode to the cathode. Now, let's look at the electrodes in more detail. An electrode is simply any electrical conductor that is used during electrolysis to convey electricity into and out of the electrolyte. Now, the electrode is usually a solid, but we have instances where liquids such as mercury has been used as an electrode. Now, your electrode can either be inert or is reactive. Now, when an electrode is inert, this means it does not react with the electrolyte or the electrolysis products, or it will not dissolve in whatever substance you have there. So we have an electrode that is inert, and we also have an electrode that is reactive. Now, two electrodes are available. We have the anode, as mentioned before. It's connected to the positive side and therefore is positively charged, and the cathode, which is connected to the negative side of the battery and is negatively charged. Now, let's look at the electrolyte. An electrolyte is any molten or aqueous substance that conducts electricity and is decomposed by it. So there are two requirements there for an electrolyte. First thing is that it should be able to conduct electricity. So if a substance does not conduct electricity, that substance cannot be considered an electrolyte. The second thing is that the substance has to be decomposed by the passage of electricity. So we have metals that conduct electricity. They are not decomposed by the electricity or the current. Therefore, we cannot call them an electrolyte. So an electrolyte has to conduct electricity and is decomposed by the electricity. So what happens here is that the moment you switch on the electrical power, positive ions in your electrolyte are going to move to the cathode because there is going to be electrical attraction, positive ions and the cathode that is negatively charged. You'd find positive ions are called cations for these reasons, because they are attracted to the cathode. And negative ions would move to the anode because they are there's electrical attraction there. Solid ionic compounds, as mentioned before, cannot conduct electricity. Why? Because ions are not free to move. The ions in a solid are fixed in the crystal lattice and cannot move from one point to another. For us to have electrolysis, it is important that the ions are free to move and they can move from one side to another. Water is considered a weak electrolyte because it partially dissociates into ions. Now let's go into electrolysis of molten compounds. When we look at a simple molten compound, we are just going to call it a binary system here because it comprises only two types of ions. We have one type of cation and one type of anion. So the moment you switch on power, the cations move to the cathode and form a metal. They're going to be discharged there, which means they receive electrons and we obtain our metal. The anion, on the other hand, will move to the anode and form the non-metal. So what happens at the anode is that the non-metal ion will lose the excess electrons and form the non-metal. So let's look at a simple example. The electrolysis of molten lead to bromide. Now, in this electrolysis, lead is formed at the cathode and bromine is formed at the anode. Now, when you are given a simple scenario of a molten ionic compound, all you do is the first part is always a metal in the name. And that substance is going to be formed at the cathode, the way it is. So you just copy it. So as in this case, we have lead to bromide. You just copy the lead part. This is the metal that is formed at the cathode. And then when you go to the anode, you take the last part of the name, replace the IDE with INE, as in this case was bromide. Now it is bromine. So let's look at a few more examples. We are going to start off with a simple one, magnesium chloride. So what do we form at the cathode? We are going to form magnesium. And at the anode, we form chlorine. Another example is aluminium oxide. What do we form at the cathode? Simple, we copy the first part, aluminium. And at the anode, we copy the last part. We just have to make sure that we get it right when it comes to the element. This is going to be oxygen. Next, another simple example, calcium nitride. We form calcium at the cathode and we form nitrogen at the anode. Next up, lithium fluoride. Think you get the trend now. Lithium and fluorine. We have two more simple ones, sodium bromide and potassium iodide. Here are the products, sodium and bromine, potassium and iodine. Now, that is simple and straightforward. You should be able to get the anode products for a simple binary substance in electrolysis. Now, what's a little bit tricky are the electrode half reaction equations. As I have mentioned before, when ions move to the electrodes, there are reactions that take place at each electrode. On the cathode side, the ion is gaining electrons. On the anode side, the ion is losing electrons. So what the electrode half reaction equations do is that they simply describe the reactions that are taking place at each electrode. At the anode, electrons are lost, like I've mentioned, and this is an oxidation reaction. At the cathode, electrons are gained, and this is a reduction reaction. It is important to always remember that the anode is a site for oxidation, and the cathode is the site for reduction. Now, let's look at the example of the electrolysis of lead-2 bromide that we looked at as our first example. At the cathode, lead-2 ions receive 2 electrons. So our equation is going to look like this. Pb2 plus 2 electrons, we get Pb. And at the anode, the chloride ions lose 1 electron. So each ion will lose 1 electron, and this is what our reaction will look like. Now, you need to remember that chlorine is a diatomic element, so it's going to form Cl2 molecules. You need to balance your equation in terms of the charge. Charge should be balanced on both sides, and as well as the matter should be balanced on both sides. For the first one, the charge on the left-hand side is 0. The 2 plus for the lead plus the 2 minus for the electrons, that gives you 0. When you go to the right-hand side, the charge is 0 because you have the neutral Pb. For the second reaction at the anode, the charge there is 2 minus on the left, and the charge on the right-hand side is called 2 minus because you have those 2 electrons. Now, let's look at a few more examples. The first one that we want to look at is barium nitride. So we have the barium receiving 2 electrons, and we have the nitrogen that is going to lose electrons, and then you make sure that your equation is balanced. So when you look at the barium nitride, you need to remember that nitrogen is in group 5 of the periodic table, and the charge on the ion is 3 minus. So it needs to receive 3 electrons. But because nitrogen is diatomic, you're going to be dealing with 2 nitrogen ions rather, and 6 electrons are involved. The next one is aluminium fluoride. Same thing, aluminium 3 plus receives the 3 electrons to give you aluminium, and at the anode 2F minus loses 2 electrons, and we are done. But there's a note that I want you to take note of. First thing is you need to get the correct charge on the ion. We use the periodic table for that. Anything that is in group 1, potassium, lithium, sodium, will have a +1 charge. Anything that is in group 2, magnesium, barium, calcium, will have a charge of 2+. Anything in group 3, for example, aluminium, the charge is 3+. We go to group 5. Example is the nitrogen, nitride. The charge is 3 minus. Group 6, oxygen, sulfur. As long as it ends IDE, the charge is 2 minus. And then the halide ions, the charge is minus. Okay, 2 more for you to do. I'm going to give you some time. You can pause the video at this point. Okay, here are the answers. For potassium bromide, K plus, group 1, Br minus, group 7. Aluminium oxide, Al3 plus, group 3, O2 minus, group 6. Okay, this is just about it. It's bye-bye for now.